Now the question really is, does sound require that there is air around us to propagate? Now, after having understood the previous module, you know that it's a very silly question to ask. Because if I plug something and if there's nothing for it to compress and expand, how exactly would our ear be able to hear sound? But just for the purpose of an excursion into thought, let's really begin to see what would happen. Because if you already understand what sound is, then you would know that the really keen ones amongst you who followed the previous bonus section will know that it's a mechanical wave. Right? It requires something mechanical to oscillate for it to propagate, which means that if that mechanical thing was removed, in this case air, it wouldn't be able to propagate at all. So if you were to understand sound as a mechanical wave that needs a medium, your understanding will be a lot more than if you remember sound requires air to travel. If there's no air, sound won't travel. As if it's very specific for sound and for air. Not really. For any mechanical wave, you need a medium, right? Otherwise, you could do a bell jar experiment where you put a bell jar and you put a little, alarm clock into it and suck out all the air from the bell jar. And then what happens is that you don't hear the sound of the bell jar, sound of the alarm anymore. Wow, that must be surprising, right? If you don't know how sound works, that would be surprising for you, but now it's not going to be that surprising, right? Now, so for the example really is, if somebody somehow were really sadistic and began to remove all the air from this room, what would begin to happen is that in some time, and the sound is coming back slowly, what will begin to happen is that you can begin to hear me again. So kind of what we require for sound to propagate is air or some other medium. Which brings us to our next question. Can sound travel through other media like liquids or solids? Can't it? Why can't it, right? So it's a question. So before we go there, we need to ask, how does sound really propagate itself, right? How does sound move? Because we know that if I pull a string like this or a rope, the wave propagates that way while the rope goes up and down. It's a transverse wave. How exactly does sound do that? So in air, we know it's a compression and rarefaction. All the air molecules are vibrating this way, so it's a longitudinal wave. Awesome. So our books always say that sound waves are longitudinal. No more questions asked, right? But it turns out that the really curious ones amongst you will ask that question always. Because whenever the word always hits you, it's a good question to ask. Really, always. It's very unlikely that always something is true. So it's a good place to begin to feel doubtful. And if you were doubtful, you're right, because sound doesn't always travel longitudinally. If you were to try to spread sound through a liquid or a gas, it would always be longitudinal. Why that is going to be true, we'll tell you in some time, or you will find out if you're really curious. But when you take sound into a solid, so can sound travel through a solid? Yes, of course. You create a vibration. In this case, if it's a solid, instead of air molecules compressing and relaxing and things like that, the parts of the solid are going to do that. Now, the interesting thing here is, in solids, sound can travel both as a longitudinal and as a transverse wave. Because solids allow transverse waves to pass through them. They are suitable for transverse waves. Now, why exactly? They have something called elasticity. Solids have a much higher elasticity. They can withstand an attempt to change their shape. Right? Solids can withstand, if you try to change their shape, they can try to withstand that. They resist a change to their shape. But do liquids do that? You pour liquid in the container, it takes the shape of that container. You pour gases, you don't even have to ask, right? They don't really resist any change. So in that way, solids are different from liquids and gases. And therefore, in solids, sound can even travel as a transverse wave. So it is not a gospel truth that sound waves are longitudinal. It's not true. Sound waves can also be transverse, as when you're talking about a solid. And great question, right? So what is this question now? Can sound travel through liquids and solids? Of course it can. Yeah, and what type of wave is sound? It is certainly a mechanical wave. In other words, it needs a medium. You cannot hear sound through vacuum, which is why if somebody took off all the air in this room, you wouldn't be able to hear me. But sound can travel both as a transverse and as a longitudinal wave. So now, being this curious and following along really well, so congratulations on learning this far in sound, which allows you to ask and answer the question, why do we have 2 ears? Now, it might seem like a silly question to begin with because most good questions sound a little silly. The question really is, wouldn't 1 ear do? Right? Now, let's begin to try and answer this question. But before we do that, we want you to get an experience of something. So I know that most of you have what's called the earphones around. Yeah, if you aren't using them, wear them. And we want you to close your eyes after you wear your earphones and really begin to experience this. Welcome back. Now, what was your experience? You were wearing your earphones and you heard a noise from one side and you heard a noise from the other side. And the question I'm going to ask you is, how did you know that the one sound was from one side and the other sound was from the other? How did you know that? What in your brain, what in your experience told you? Because you know that it was a earphone. It wasn't really, all the sounds were created by the earphones. You know that it's not really that the sound came from that side, right? We could even create even more interesting experiences. But the question really is, how does your brain know this? How do you know that it's coming from a different side? You might argue that one side is louder than the other. Yeah, but that's only part of the story. And the real deal is here, because if you were to take this and logically extend it, you would find out so many more interesting things. The first thing we need to understand is our brain or our ears are extremely sensitive to sounds timing. So you can differentiate sounds within like one fractions of seconds, which means that what your brain really does is if you have a sound coming from here, it's going to reach this here in a particular time. In other words, sound, as you could see, right? Sound propagates through a medium, right? Does it do it instantaneously? You could see that, right? You pushed a slinky, it took some time to travel. So what exactly determines the speed of sound? We're going to see, right? But we know it has some speed, yeah? So it's going to come and reach this here, and it's going to take some more time to reach this here. So what does your brain do? Takes the time difference between these two sounds. If this was occurring before this, the sound must be exactly over here, right? Somewhere over here. Now this time lag was lesser and lesser and lesser. You know the sound somewhere here and somewhere here and somewhere here. If it's zero, you know it's probably somewhere in the front or somewhere in the back or something like that, very symmetric. Or if this here begins to hear it faster, then the sound starts coming over here. In other words, you know it's going to be somewhere along this side. And the maximum difference in time means that it's going to be exactly somewhere over here. Isn't that amazing? Yeah. In other words, evolution is extremely efficient. If it keeps two things if it keeps 2 years, it will not do it without a purpose. Rather, without a purpose that can only be achieved by 2 years, because any other thing can be achieved by just 1 year. But this particular functionality of being able to take the time difference between these 2 years and thereby predict where the sound came is very useful, because we were hunters, right? We needed to see where it came, or even if somebody was chasing us, we needed to figure out where the sound came from. Now, the really interesting thing here is that a scorpion does something very similar, but at a much more efficient, nuanced level, because we use, say, 2 ears. It has about 6 legs along with its 2 antennae, or what it's called the claws. So each of its 6 legs perceive waves on the sand. So if it's a desert scorpion, 6 legs put into the sand, measuring waves on the sand. So we might not be able to see this, but when an animal or a little prey, as far as scorpion is concerned, moves along the soil, along the sand, the desert sand rather, not really soil, what you observe is that little waves are created. And the scorpion, by figuring out which leg the wave reaches first and which leg the wave reaches last, takes these time differences and almost exactly pinpoints where the prey must be and dashes towards it. Really interesting, right? So we're kind of doing the same thing, except at our level, because we're not really trying to dash towards prey that much. Yeah, we have other vision, other things that are more useful for us. We have our sight, which is our predominant sensory perception, comes from sight. So great. So one of the questions we've answered and unlocked right now is, why do we have 2 ears? It's a pretty interesting thing that we found out. Why we have 2 ears? To calculate where the sound's coming from. Now the question is, doesn't sound have a lot of characteristics? Because otherwise we wouldn't be able to differentiate good music from really bad music. We wouldn't have a nuanced sense of taste that tells us what good music is, or what differentiates. It's a big question actually to ask what is good music and what is just noise. So, but we're not going to go there. We're going to go into something much simpler than that. And the question is, we want you to watch this now. Now listen to this. Now the question really is, what is the exact difference between each of the sounds that you hear? What exactly was the difference? Was it the loudness or was it something else? Because we're kind of striking each with an equal amount of force, which is not really very different. So what else is different about each of the sounds that come from this? That's the question for you. Now you heard the different sounds, right? And there was something that differentiated each strike on the glass. Each glass produced a sound that was significantly different, just characteristically different. What was different between each of the sounds produced? What exactly was different? Because now we can't talk about sound as if it's an unknown entity, right? We know what it is. We know it's just compressions and rarefactions moving through the air Therefore, if I hear a different sound from one glass as compared to another glass, something about the wave must have been different. What exactly was different? That's the question. Now you also saw, now let's watch one more thing, right? Let's watch this and hear it. The question here again is that how exactly were each of the strings different from one another? If all of them are going to compress air, then how would you just hear them differently? What exactly is different between them? Before we go further, the question is, if I were to speak loudly or to speak softly, you would know the difference between the two, wouldn't you? Right? Between a very, very loud noise and a really, really soft, a very low volume voice. So the word volume makes sense to us. We change it on our TVs. What exactly is volume got to do with our understanding of sound, which is as a wave? And another question is, well, if I were to speak and if my pitch, as we call it, right, it's a high pitch sound. So if the pitch were to go higher and higher and higher, or if the pitch were to go lower and lower and lower, then what is this pitch that we call in real life? In real life, we say it's a high pitch sound, it's a low pitch sound, it's a bass sound, it's all that. How exactly do we define it in terms of the wave? So these are the set of questions we're going to start with, and we're going to handle them by going into our picture of sound as a wave, right? So we know that sound is a set of compressions and rarefactions, as you can see, and a better way to represent that is as waves in this format, where you can see each compression as a peak and each rarefaction as a trough. So a crest and a trough. The peak, we usually call it a crest. Great. So now with this visualization, which you already know about, we're going to define certain quantities. So we're going to take that wave, keep it in front of us, and we're going to define certain quantities. The first one being the distance between two crests or two troughs. You already know they're going to be equal, right? The distance between two crests and two troughs is going to be equal, and that particular distance is what we're going to call a wavelength. So it's the length of this wave. Yeah. So it's why we define these quantities, we'll find out. Okay. So that's the wavelength. Great. Now another thing we're gonna define is how many such crest trough pairs. We take one crest and a trough. That's like one wave, because after that that keeps repeating. So that one crest and one trough in 1 second or in 1 unit of time, usually it's a second, how many times does it occur? So if you have 3 of them occurring, right, in a second, right, 1, 2, 3, then you have a frequency of 3. If you have 4, it's 4, and it's beginning to get obvious now, isn't it? So your frequency, which is the number of crests and troughs, crest plus troughs, yeah, in a unit of time, usually a second, and wavelength is the distance between two crests or two troughs. And now you have to calculate something called time period, right? Yeah, because usually we can calculate how long it's going to take for one wave to complete, right? For the period to get over and the next one starts, because you can see that there is some periodicity here, right? One thing starts, then one more thing starts. It's symmetrical after a point of time. You start one, it again continues. So the question is, how long will that take? Now it's very easy to calculate that that's going to be exactly 1 by the frequency. Now why is that true? Let's do a little talking about this. So let us say that I have 5, from now let's just call it waves, okay? Yeah, a crest and a trough put together, let's call it one wave. So therefore, let's say I have 5 waves in 1 unit of time, in 1 second. Then what is my frequency? Yeah, 5 in 1 second. Therefore, the frequency is 5. But now if I were to ask you, what is the time period? In other words, how long does one wave take? This goes back to the old question, right? 5 mangoes cost 20 rupees. How much does 1 mango cost you? Yeah, you would do this pretty easily, wouldn't you? Yeah, if 5 mangoes cost 20, then 1 costs, that's right, 4. Now, how did you do this? It's called unitary method. It's something very similar here. If 5 waves take 1 second, then 1 wave will take 1/5 of a second, right? That's exactly what it will take. If 10 waves take 1 second and the frequency is 10, then how much will the time period be? 1/10. Do you see the pattern already? Frequency is going to be 1 by the time period, or time period is going to be 1 by the frequency. So they're related as inverse. And it's very logical as to why that is true. So we've defined 3 quantities here. Time period, the time one wave takes to complete. Second, the frequency, which is the number of waves in a particular unit of time, usually a second. And wavelength, which is the distance between two crests or two troughs. Great. Now there's one more quantity that we're going to define for you, right? Now if you have this wave, and could you draw it in a way like this, but I could also draw one more on top where it's much larger, right? In this case, if it's much larger, then we say that the amplitude is larger. In other words, the displacement of this from that line, from that mean line, is larger than if it's a much smaller amplitude. So amplitude tells you how far away a crest or a trough is going to be from that mean line. And as far as you're concerned, what does it translate to as far as sound goes? How much are we compressing and how much are we pulling air apart? So if you have like normal pressure of air, high pressure is going to be how much high? Right? It could be slightly higher pressure than normal pressure, and the rarefaction could be slightly lower pressure, or it could be much higher pressure and much lower pressure. So if it's much higher, then the amplitude is going to be much larger. So that's the physical significance of what we draw here as amplitude, right? And as far as your frequency goes, as far as you connect it to sound, how does it go? How many compressions per unit time? Or how many rarefactions per unit time? The wavelength, the distance between two compressions. And the time period, of course, is how long does one compression and rarefaction take to propagate. So we have a connection between sound and the waves. Now all we have to do is connect this to our real life words, which are volume and pitch and certain other words. So let's begin to do that. So as you begin to see this wave here, we want you to notice what begins to happen as we begin to increase our volume. So as the volume of what I'm speaking begins to increase more and more and more and more, what changes here? Right? That's right. Only the amplitude changes. So what we call volume in real life is, as far as the wave goes, it's the amplitude. The amount of compression and rarefaction, and only that changes, as you can see. Now, if I were to increase my pitch more and more and more, watch what begins to happen. The larger and larger the frequency becomes, the closer and closer these waves get. In other words, their wavelength reduces or their frequency increases. The frequency is increasing. Or if I were able to make my volume or my voice lower and lower and low pitched, the pitch is going to become lower and lower and lower and lower. Watch what begins to happen. The wavelength begins to increase or the frequency is reducing. Right? That's what you observe. So frequency for the wave is what we in real life call pitch of the sound. Amplitude is what we call volume. So that's pretty interesting what you observe here. But what's even more interesting for you is that let's say I take one instrument, right? Let's say I take a guitar and play a particular note on it. But in order to talk about a note, we need to talk about what a note is and what a tone is. And we're going to do that right now. If you have one particular frequency, you take a wave of a particular frequency, that's a particular tone. You take a different frequency, it's a different tone. So a sound that's made up of one frequency is called a tone. And if I were to put together a few frequencies, which have a special characteristic to go together, and then produce a sound, it's called a note. So a note is usually made up of a few frequencies. Some of them, one called the fundamental frequency, some of them are overtones and some of them are undertones. If you're the really keen ones amongst you, can go and find out how these work in detail. If you're already a musician, then you'll know what I'm talking about, even though I'm not one. So what begins to happen here is that if I were to take, so you know what a note is and what a tone is. I could now take two instruments and play the same note, right? Both of them are going to have the same frequency in our sense of the word, right? So a note is going to have the same frequency. But the sound from a guitar is going to sound very different from the sound from, say, a flute. So if their frequencies are same, let's make their volumes also same, then what exactly differentiates them? Now, while you hold this question in your mind, the real question is, we played what's called the Jal Tarang in different classes. We filled different amounts of water, played it, and the sounds were different. What exactly was different? What do you think was different? Was it the volume or the amplitude? No, it was the frequency or the pitch. The pitch varied. In other words, when you hit on these glasses, the amount of air available to vibrate is different in each of them. Therefore, the pitch that's produced is different. The similar is true with the guitar, because you took it and plucked each of the strings, they all produce sounds of different frequencies. Each one was different because the thickness of those wires was individually different. So the frequencies with which they vibrated was different, even though the volumes would have been pretty similar. So now that you've come this far, the first question we promised to answer you is, would all animals and human beings agree as to what sound really is? Well, the answer is no. We've all evolved to consider different parts of this entire spectrum, as we can call it, right? Low frequencies to very, very high frequencies. And each of us, based on what we require, because evolution, like I told you, is very, very lazy, or you can think of it as very efficient. It won't do things that are unnecessary. So take some little chunk of it. We call this part of it sound of the entire spectrum, very, very low frequency to very, very high. We take this little piece called 20 to 20,000 hertz. Now, what is this new word? Right? It is just the unit with which we measure frequencies. So, if the frequency is 5 per second, we call it 5 hertz. So, what is the unit of its second inverse? Yeah, 1 by second. So, we also call it hertz in memory of one of the great scientists. So what we're going to do is we take 20 to 20 kilohertz. So 20 hertz to 20 kilohertz is what we take and call it sound. Dogs take frequencies that are much higher. Snakes take frequencies that are much lower. Whales and elephants take frequencies much, much lower. So we probably don't hear elephants and whales communicating because they're communicating at sounds that we don't even consider sound. Right? So that also will answer your question as to why this is something we won't hear. Look at the frequency of this, right? How many times a second? Yeah, not much at all. So if we were to make it go really, really fast, thereby reaching speeds that are between our hearing range, then we might be able to hear this. Might be. Yeah, increase it fast enough, then we can hear it. Yeah, but right now what we're doing here, a snake would hear. Because we know that all the snake charming is a bit of a joke, because the snake doesn't really hear these frequencies. The snake doesn't hear our frequencies. So what tune we play, it hardly cares about. But what it does care about is the way in which the charmer moves it around, because that frequency is what it follows. The charmer taps his foot very gently, and that frequency it follows. So it's one of these occasions where we attribute a cost to something where the actual cost is very, very different. So one of the questions being, what is exactly this thing called quality of sound? Because the frequency could be the same, the amplitude could be the same, everything is same. Then how do I differentiate between a sound from a flute to a guitar, or between person A and person B? It's called what we call the quality of sound. Now we found out that it's a pretty complex thing to figure out what this quality is, and the really keen ones amongst you will notice that each note that we call has overtones and has undertones, right? So all these put together give us one sense of sound, a note. And this particular frequency is called the fundamental frequency, but it's not the entire spectrum. So what differentiates, say, a guitar's note from a flute's note is that the overall composition looks similar, but this internal composition, it's like if I were to make 40, I want to make the number 40. I can make it by adding 20 and 10 and 10, or I can make it by adding 10, 10, 10, 10, 4 times. Now both finally would look like 40, right? But if you go deeper inside, you'll notice that the things that make them up, right, are different. Our ear picks this up. It picks up the different undertones and overtones in these two, and it gives us a sensation of what we call quality of sound, or timbre of the sound. It's a very interesting concept to go into it, because it's mentioned, we really thought it's important to understand. Now the next question being, now that you've come this far, you've unlocked one more really, really interesting question, which is the matchbox phone. How does this work? Right? You speak into a matchbox and somebody can hear far away. The ones who don't believe this, by the way, you should try it. Yeah, you take a rope, a little thread, and tie it down, and that's what's going to happen. Now what do we know right now? That the speed of sound depends on the medium. Now typically, we're going to tell you why later on, but typically sound travels slower in gases, faster in liquids, and fastest in solids. Yeah, it's a property, it's got to do with the elasticity that solids have, right? The tendency of them to get back to their original shape quite fast. Now, what this means is that sound's going to travel a lot faster in the thread of the matchbox than if the thread wasn't there and you try to speak it in the air. So a person speaks it here, another person tries to hear it here. If there's only air in the middle, it's going to go a little slow and it's going to get dissipated. Yeah. One of the things about this is that you let something go through the air, it's going to eventually get dissipated, because each ball, if you imagine sound as a ball of particles, balls of particles floating in the air, each ball hitting the next, compressing and expanding, then sometimes the ball hits, then it doesn't really bounce off that far, right? You've seen this in real life, haven't you? You drop a ball down, it bounces, doesn't come back to the same height, it keeps like going further and further and further down. It's called damping. Yeah, that's what happens here. The sound gets damped off after a while, doesn't reach there. But if you put a thread in the middle, sound's traveling quite fast in the thread, so the damping becomes a lot lesser. So sound travels through the thread, reaches the other person's ear a lot faster, thereby doesn't get dissipated or damped as much as it would if there's only air. Makes the matchbox phone a really interesting device to use. Now all the things we've spoken about in this particular module, about the characteristics, frequency, amplitude, wavelength, time period, are not restricted to sound. And that is something we want you to know. It is true for any wave. It's very, very general. The wavelength multiplied by the frequency will give the speed for any wave. Even if it's a non-mechanical wave, it doesn't even need a medium to travel. But if it's a non-mechanical wave, its speed is, of course, going to be a constant. It doesn't need a medium to travel. So we're giving you the general larger chunks over here. So what you have learned here need not be restricted to sound. They are general for any wave, whether it's frequency, amplitude, time period, or wavelength.